Hi, welcome back. Today's video is on Magic Pulleys, or what to do when there's a pulley in your problem. So let's go ahead and get started. Okay, so a pulley simply bends the coordinate system. Okay, so we want to derive a formula for the acceleration assuming that the table is frictionless. Okay, so I'm going to bend my x-axis at the pulley. I'm going to draw my free body diagram. There's box 1. There's the cable linking box 1 with box 2. Box 2 has the force of gravity, its weight. So there's going to be that force, m2 times g. M1 will have a normal force, and it also has its own weight, m1g. Now what we're going to do is we're going to sum our forces in the x direction. I'm going to notate that that's the x direction. I'm going to identify what my system is. I'm just going to draw a little dotted line around. That's my system, which means that the tension from the cable that's in the middle is an internal force, and we get to ignore it during our calculation for the acceleration. Okay, continuing on with the second equation, I'm going to use second law equation. Well, what's the mass? Well, what's the mass of our system? Well, we have two blocks, M1 and M2. So it's going to be M1 plus M2. That's the mass of our system. Times the acceleration of our system. And that's equal to the forces that are acting on our system in the x direction. Well, looking at my free body diagram, the only force that we have acting in the x direction is the weight of block 2, m2g. Now, the last step is to solve for the acceleration. And so I'm just going to do the algebra on this equation here. Acceleration is equal to m2g divided by the sum of the masses, m1 plus m2. And that's how we determine our acceleration, and that is for the entire system. Next up. Okay, for this system, it's a little bit more complicated. Follow the same steps. We make a new x-axis that's bent at the pulley. So that's our x-axis. And when we stretch it out, we have M1 connected by the cable to M2 to M2. Now we're going to do our free body diagram for this system. Well, on M2, the only force that's external to the system is its weight, m2g. The gravity on M1 is actually acting like this. And the normal force is acting like that. And if you were to rotate my M1 box, you would see that that's the case. Now I'm going to sketch in my components of gravity on the M1 box. The angle here is theta. The component, the vertical component of gravity is m1g. The side is adjacent to the angle, cosine theta. And the side opposite is m1g sine of theta. Now I can go right to putting together the second law equation for this system. sum of our forces in the x direction is equal to mass of the system, m1 plus m2, that's the mass of our system, times the acceleration of our system, and that's equal to the forces acting in the x direction. Well, in the positive x direction we have m2g. In the negative x direction we have this component of gravity, and that's m1g sine theta. And that's in the negative direction, so it's minus m1g sine theta. And we've been asked to find the acceleration, so let's go ahead and just solve for the acceleration. Acceleration in the x direction, let me notate that properly, is equal to m2g minus m1g sine theta divided by m1 plus m2. And I'm going to clean this up a little bit. I'm going to simplify it, factoring out a g, and that would be m2 minus m1 sine theta, this whole thing times g, all over m1 plus m2. And this is our acceleration. Okay, take a good look at that. It's just following the same steps. We add a little bit of a challenge by putting it on an inclined plane, but I'm sure you can handle this. Let's see what's up next. Oh, now we have to derive a formula for the tension in the string. We want to find out if the string is going to break. So I'm just going to work through the part of the problem to find the acceleration, because I know that I'm going to need that. I need to know what the acceleration of the system is. So I'll work through that really quickly, and then we'll have the acceleration and then continue on. Okay, now that I have my acceleration, I can use that to find the tension in the cable. So I'm just going to look at one of the boxes when I do this. One of the boxes will be enough to find the tension. So my system now is going to be box 2. And box 2, I'll keep the same orientation that I had for the first part of the problem. So box 2 has a tension from the cable, and that's pointing in our x direction, left x direction, and it has its weight, m2g. Okay, sum our forces, and that's equal to the mass of the box, which is m2, times the acceleration. I'm just going to put in placeholder variable acceleration, and that's equal to the forces acting on it. So in the positive direction we have m2g, and it's positive because at the outset we said that this was the positive x direction, minus tension. So I have my tension is equal to m2 times g minus the acceleration in the x direction. Well, I need to substitute in my acceleration in the x direction. So at this point it will be m2 times g minus g times m2 minus m1 sine theta, all over m1 plus m2. And I can reduce this further by factoring out the g. So this is our final solution. It looks like a mess, but if you know the mass and the angle, it's not too hard to find out what the tension is in that system. Let's see what's up next. And now I think you're ready for your free response problem. Good luck. We'll see you next time.